Okay, so this is the second set of notes in this unit. We are moving from sequences to series. Okay, so a series is basically taking a sequence, and instead of just listing the terms, you add the terms. So we're going to add all the terms from n equals 1 to infinity of the sequence. Okay, for shorthand, if we leave off the bounds, the n equals 1 and the infinity, we can write the series just like this. Sometimes the BC exam does. It assumes that if the bounds are not listed in the sigma notation, that it is n equals 1 to infinity. So one of the big things that we test for with a series is to see if it converges. So basically the question is that if you take this infinite sum, does it add up to a finite number? And it seems like odd that if you actually take an infinite number of things and add them up, you would get a finite number, but in fact there's some pretty common examples that work. Like if I take 1 plus a half plus a fourth plus an eighth and so forth and so on, so we're just going up by powers of 2 in the denominator, this actually sums to 2. We'll prove that later in the course. That's a geometric series with a finite sum, so it's convergent. So this is kind of a kind of simple idea of this, but in order to get at this, we actually have to give some actual more substantial definitions. And the first definition that we need is what's called a partial sum. Okay, so when you have a partial sum, the kth partial sum is the sum from n equals 1 to k of the elements in the sequence. So, like, if I have the sequence just 1, 2, 3, 4, etc., the fourth partial sum would be the sum from n equals 1 to k. So this is my a sub n of a sub n, which would be 1 plus 2 plus 3 plus 4. And that partial sum, let's see, that's 3 and 4 is 7, and 2 is 9, and 1 is 10. So the fourth partial sum of this series is 10. Okay, so this gives me a way to talk about partial sums and also to create a new sequence. You would have like the first partial sum, the second partial sum, the third partial sum, the fourth partial sum, so forth and so on. So S sub n is a sequence of partial sums. So this is where we're going to grab to get an idea of convergence. Okay, so we're going to define convergence of a series, right? So convergence and also divergence of a series. So this is of a series as opposed to a sequence, right? So what we're going to do is we're actually going to use the sequence of partial sums. So if each partial sum is the sum from n equals 1 to k of a sub n, and this sequence S sub n is convergent, so if that sequence has a limit, and you can refresh the idea of a limit of a sequence in the last video, right? So we would say that if that sequence is convergent, then we say that the sum is convergent. So if the sequence of partial sums is convergent, then the series itself is convergent. And we say that the sum, the series itself, is equal to the limit of the partial sums as n goes to infinity. So if I take the limit of the partial sums, I get the value of the series, and that would be when the series is convergent. Otherwise, if the series of partial sums is not convergent, then we say the series diverges. Okay, so what we're going to basically be doing over the next several classes is coming up for ways to test when our series is convergent and when do they diverge. And this is going to be like a battery of tests that we come up with and are used to test almost every sequence almost every series for either convergence or divergence. The one that we're going to hit today is actually what is called the divergence test, and it's actually pretty simple. Okay, so the divergence test makes a simple statement. It says that if the limit as n approaches infinity of a sub n, so this is just the limit of the sequence, not even the limit of the series. If the limit of the sequence goes to something other than 0, then the series diverges. Okay, so the idea here is that the sequence itself has to be getting smaller and smaller and smaller. Otherwise, this thing is going to get larger and larger and larger and go off to infinity. So this thing actually has to be going to 0 in order to have convergence. Now, this is only a test for divergence. It will not get me convergence. There is no converse to this. It's not if the limit goes to 0, then it converges. That's not true. But if the limit does not go to 0, then we know that the series diverges. So let's work a couple of examples here. If I have the series of 3n over 2n plus 1, well, we know that the limit as n approaches infinity of 3n over 2n plus 1 goes to 3/2, and this is not 0. Therefore, this series, 3n over 2n plus 1, diverges. So this thing, when you start adding up its terms, is going to go off to infinity. It's not going, the sum of the sequence of partial sums is not going to converge on any given number. So here, because the limit is not equal to 0, I get divergence. Okay, so the second example that we're going to give here is something that's known as the harmonic series. And we've seen the harmonic sequence. The harmonic sequence is the sequence of 1 over n. The harmonic series is the sum of the 1 over n's. Now note, if I take the limit as n approaches infinity of 1 over n, I in fact get 0. But according to the divergence test, this tells me nothing. Okay, so this tells me nothing because the converse of the divergence test doesn't hold. Okay, and in fact, this series, though the limit goes to 0, it actually diverges. And we'll show that in a later class that the harmonic series does diverge. But ultimately, here we know nothing when we get the limit being equal to 0. This test is inconclusive. Okay, can't make that more clear. So you get the limit not going to 0, we get that the series diverges. Limit going to 0 tells us nothing. We need to do more investigation because the test is inconclusive. Okay, so in summary, a series is the sum of the elements of a sequence. If the sequence of partial sums converges to a limit, then the series converges to that limit. And if the sequence that is being summed by the series does not go to 0, then the series does not converge. But note, again, the converse of this is not true.